Hello. So in this video, I am going to talk to you about another important concept in probability, which is joint probability. So to understand that, let us just take a simple question. We will try and solve this question, and in that process, know what exactly is joint probability. Okay, so let's say we have an unfair dice. Or rather, let's consider an unfair coin. And the unfair coin has 1/3 probability of showing heads, and therefore the probability of tails is going to be 2/3. And so the experiment here is that you toss this unfair coin 3 times. Okay, and the question that we are wanting to answer here is, what is the probability that you will get H, H, and H? All right. So meaning getting heads in the first toss, heads in the second toss, and heads in the third toss. So now we are no longer going to draw any tree diagrams, just that it is important to note that there are 8 different possibilities, and H, H, H happens to be just one out of these 8 possibilities. And we have already calculated this probability earlier in one of the earlier videos, and the probability of getting H, H, H in this unfair coin is going to be 1/3 times 1/3 times 1/3, and that is going to be 1/27. All right, so we already know this, but where is the idea of joint probability over here? So the question is, why is it 1/3 times 1/3 times 1/3? So in order to understand that, let us do something like this. Let us declare an event A, and we will define it as the first toss being heads. We'll define another event B, which is the second toss being heads, and another event C, which is defined as the third toss being heads. And when we ask the question as to what is the probability of getting H, 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 we are essentially asking what is the probability of A, B, and C happening together. So this kind of a probability is basically called a joint probability. We are asking what will be the probability that all of the 3 events A, B, and C will happen together. And you could also write it as probability of A and B and C, but it can be simply written as A, comma B, comma C inside the parenthesis. So this is a general idea of joint probability. And since each of these tosses are independent and the outcome in one will have no bearing on the outcome of the other, we can multiply the probabilities of events A, B, and C, and that is why we have 1/3 times 1/3 times 1/3, and that is why it is 1/27. All right. Okay, so what we will do is we will take another problem just in order to look at the joint probability a little more carefully and critically. So let me tell you what the other problem is. Let's say we have a fair dice now. We have a fair dice. And in fact, we don't have one, we have actually 2 fair dice. All right. Let's say one is red colored and the other one is green colored. Right. And we can ask the probability question that what is the probability that when you roll these 2 fair dice, what will be the probability that you get 5 in the red die and and 6 in the green die. Okay, we can always ask this probability. What is the probability that I will get 5 in the red die and 6 in the green die? So here again, before wanting to look at it from the mathematical point of view, let's look at it using a picture. And what you are seeing here is a checkerboard. So I have green die on one axis, red die on one axis. And the problem is, what is the probability that you get 5 in the red die, 6 in the green die? So here, the sample space omega comprises of 36 different possible outcomes. Okay. For instance, here you have 2 in the red die and 2 in the green die. In this cell, you have 5 in the red die and 3 in the green die. So here, sample space omega and mod of omega is 36. All right. Now, when we say that, if you look into the question, what is the probability that getting 5 in the red and 6 in the green? Now let us look at which of the squares here satisfies the criteria, getting 5 in the red and 6 in the green. And that is this particular square, right? 5 in the red and 6 in the green. And so how many possible outcomes where you can have 5 in the red die and 6 in the green die? There is only one. So here mod A is equal to 1. All right, where A is defined as an event of getting 5 in the red die and 6 in the green die. And so therefore, the probability that I am going to get 5 in the red die and 6 in the green die is going to be equal to mod A divided by mod omega, and that is equal to 1 over 6. Why? I mean 1 over 36. Okay, there is 1 over 36th chance that when you roll these two fair dice, you will end up getting 5 in the red die and 6 in the green die. So the answer to this question is 1 over 36. All right. But now let us look at it in a different way. We could have even answered the question in the following manner. Let's define an event A where we say A is defined as getting 5 in the red die, and another event B as getting 6 in the green die. And so now asking, what is the probability that I will get 5 in the red die and 6 in the green die will be equal to the joint probability of A comma B, right? And I can now use the product rule. I can say that this is nothing but probability of A times probability of B. Okay, and then let's look at what are each of these components. What is the probability of A? How is A defined? Getting 5 in the red die. What is the probability of getting 5 in the red die? It is 1 by 6. What is the probability of getting 6 in the green die, which is P of B? That is equal to 1 by 6. And so therefore, again, we have the same answer, 1 over 36. So this is how you have the idea of joint probability come into the picture when you are asking the probability questions such as the one shown over here. But then let me put another question, and so that is going to allow us to understand how things can be a little different and a little complicated. So let's look at the other question. Now, say for example, let's say I am again considering a dice in the example. Okay, so again, your problem statement relates to a dice, and to make matters a little simpler, let's consider that it's a fair dice. Okay, it's a fair dice where you have 1/6 chance of getting each of these numbers 1, 2, 3, 4, 5, and 6. Okay, now we are going to answer questions related to two different events. Okay, first let us answer the question, what is the probability of getting an even number? Okay, well, you don't really have to do much of calculation. Here intuitively, you can just tell me that the probability of getting an even number is half, because you have these possibilities 1, 2, 3, 4, 5, and 6. This is the sample space omega, and the even numbers are 2, 4, and 6. So therefore 3 over 6, that is half. All right. So this is one thing that you have. Okay. Now let us ask another question. What is the probability that you will get a number which is less than 6? Okay. Now again here, this is the sample space omega, and the event that you are talking about, that is getting a number less than 6, relates to 1, 2, 3, 4, and 5. 5 out of the 6 possibilities. All right. So the probability of getting a number less than 6 is going to be 5 divided by 6. Okay. So far so good. Right. But remember, note that what if I ask this question? I ask, what is the probability of getting a number which is even and less than 6? What is the probability of getting a number which is even and less than 6? Means both simultaneously these two events are happening, that it is even and that the number is less than 6. Okay, now let us try and solve this problem going by the same technique that you used in the previous problem. So here let us define the two events. A is defined as getting even number. Let us define B here as getting a number less than 6. All right. And so asking what is the probability of getting even number and a number less than 6 is nothing but joint probability of A comma B. All right. Which, if we were to use the previous calculation, will be probability of A times probability of B. All right. Now let's see what is probability of A here. Okay, what is A? Getting an even number, which is 1/2. So let's put half here. Times probability of B. What is B? Getting a number which is less than 6. And so that is 5 by 6. And there you have the answer is 5 over 12. Okay. But then look, there is some sort of a problem, isn't it? Well, let us see what would have happened if you would have answered the question based on pure intuition. So you have 1, 2, 3, 4, 5, 6, the sample space omega. So mod omega is 6. Let us try and find out which of these numbers over here satisfy both the criteria that the number is even and at the same time the number is less than 6. Well, if the number is to be less than 6, then this 6 is not there because it has to be a number less than 6. So what remains is 1, 2, 3, 4 and 5. And let's look at how many different kinds of numbers are there which are even now. It's only 2 and 4. Alright, so only 2 and 4 are the possible outcomes in a fair dice that satisfy the criteria that it is even and at the same time it is less than 6. So what would have been the probability of that? So the probability of getting a number which is even and less than 6 has got to be 2 divided by 6, and that is 1/3. 1/3 is the answer here. But then you got it completely wrong. Alright? Now, what is the problem? The problem is that in this question which we solved, okay, where we applied the rule that probability of A comma B is equal to P of A dot, which is multiplied by P of B, here we could apply the simple product rule because getting 5 in the red die and getting 6 in the green die, they are independent events. The outcome in the red die will not impact the outcome in the green die and vice versa. So these being independent events, I could simply use the product rule and get the correct answer. But if you analyze the problem here, you will realize that getting a number even and getting a number less than 6, if you consider these two events, they are actually not independent. Okay, and that is why you are getting this weird result over here, right? These are not independent because less than 6 is including these 5 numbers, and getting even also includes 2 and 4. So they are not independent. One has got something to do with the other. So in that case, what kind of operation do we use to calculate the joint probability? Here, in this case where the two events under question are not independent, there the probability of A comma B should be probability of A given B times probability of B. Okay, so in simple language, what does this mean? Probability of A comma B, meaning the joint probability of A and B is equal to probability of A given that B has happened times probability of B. Okay, and this thing over here is basically what is referred to as the conditional probability. Probability of A conditioned on the fact that B also has happened. Okay, so let's solve this problem here. First, let's put probability of B. What is the probability of B over here? B is getting a number less than 6, all right, and that is 5 divided by 6. So now, how does one calculate probability of A given B? What is B over here? B over here is getting a number less than 6. Now, when we say that B has already happened, meaning that you are getting a number less than 6, then our universe, which was earlier 1, 2, 3, 4, 5 and 6, now shrinks to 1, 2, 3, 4 and 5. Now that the number is less than 6, what is the probability of getting A? That is getting an even number. Now you can see clearly the two even numbers in these 5 numbers is only 2 and 4. So therefore, the probability of A given B, meaning getting an even number given that the number is less than 6, is 2 out of 5. So let's put that down. 2 over 5. And so the product of 2 over 5 and 5 over 6 is 2 by 6, and that is equal to 1/3. And so this is what exactly matches with your intuitive answer to the problem. Okay, so what is the take-home message here? The take-home message here is as follows. The joint probability of P of A comma P will be equal to probability of A times probability of B if A and B are independent. All right, if A and B are independent, but if they are not independent, then it will be probability of A given B times probability of B. All right, and this will happen if A and B are not independent. Okay, now just a small note. This is again a more basic relationship. You can always go ahead and use this relationship. It's just that even if the situation is that A and B are independent, then the probability of A given B actually reduces to probability of A. Just think over it, and then in the next video I'm going to come up with some other important concepts in probability.